A student in a lab uses the apparatus as shown. So you can see the apparatus which is used by the student to determine the specific heat capacity of aluminium. So a voltage supply, measuring instrument, electrical heater are there. Mass of aluminum block, initial temperature, final temperature, and electrical energy supplied. The first one is define the specific heat capacity. What is a specific heat capacity? The specific heat capacity, you have to learn this definition. It is energy required to change temperature of 1 kilogram substance by 1 degree centigrade or 1 Kelvin. That is the definition of a specific heat capacity. You have to memorize this definition, learn this definition. Use a reading above. We have to calculate the specific heat capacity of aluminium and state the equation you use. Because there's a change in temperature. So whenever there's a change in temperature, which equation we use? We'll use the equation that energy supplied or removed is equals to Cm delta T. So if I need a specific heat capacity, so as a specific heat capacity is a subject, so it will be energy divided by mass into temperature change. The energy which we supplied, that is 23,800. The mass is 0.93. And temperature change is always like the final, the higher temperature, because it should be final minus the higher minus the smaller value. So it is 41.3 minus 13.1. So when we simplify, like substituting the value, this will give us the value for specific heat capacity for a block of aluminium. So when you substitute these values, the answer will be 907 or 908, 907.5. So 907.5 joules. The unit is joule per, because the mass is kilogram here, kilogram, and temperature we took in degree centigrade or Celsius. So joule per kilogram degree Celsius. So whenever remember in a question, if we have a change in temperature, a temperature change, we always use this formula. Because the student knows it is a good scientific practice to repeat the experiment. So he just keep all the things same, and he just carried out at a different temperatures. Use these figures to calculate. So only the thing what is different, like we need again the temperature change. So formula for energy, whenever there is a temperature change, it is Cm delta T. This will be delta T, and we need a specific heat capacity. So it will be energy divided by mass into temperature change. It's specific heat capacity. Energy we supplied same 23,800. The mass is also same. There is no change in the mass. That is the same block is there 0.93. And temperature change for this part, it is 62.1 minus 41. So when we substitute, it will be 1212.9. So specific heat capacity is 1212.9. The unit is joule per kilogram degree centigrade. So when you compare the two temperature changes, they're different from each other. Like the second, when student repeat the experiment, temperature change is smaller for the same amount of heat energy. And when he did the first time the experiment, the difference in the temperature was more. It's about like 28 degrees. So what is the reason why here we have a greater difference in temperature in the first experiment for the same 23,800 joule, and the second experiment of a smaller temperature change. The main difference is the starting temperature, because the first experiment, the block was at 13 degrees centigrade or 13.1. But the second experiment, the block was at 41.0 or 41 degrees centigrade. So when we supply same 23,800 to both blocks, or the same block, but at different initial temperature, because this one is initial higher temperature, so it will lose more heat energy to the surrounding. This will lose, but small amount of heat energy lost to the surrounding. That's why the two values are different from each other. So student did not make any mistake when taking the reading, suggests why the second value of a specific heat capacity is greater than the first. So what is the reason for that? The reason is, when student did the first experiment, he started, the temperature of a block was 13.1 degree. When student did the second experiment, he started with 41 degrees. 41 degrees, it's a high temperature, so it was losing more energy to the surrounding. So when we supply 23,800 joules, the rate at which the energy lost to a surrounding is higher, because when the temperature is high or a greater temperature of an object, more energy lost to the surrounding. Where in this one, 23,800 joules is supplied, as it's at low temperature, so it is because like room temperature might be 25, so it will absorb energy from the surrounding rather than losing energy. So the second block was losing energy, greater amount of energy to the surrounding. That's why its temperature change was small. So when the temperature change is small, the specific heat capacity will be higher, because we have the formula: specific heat is energy divided by mass and temperature change. Small temperature change, higher specific heat capacity. So the second block at high initial temperature, lose heat energy or lost heat energy to the surrounding. Which give a smaller temperature change. Is it clear, this one?
Yes, sir, clear.
The next part, they ask how we can improve these, such experiments can be improved. So how we can improve these experiments? If we don't want the heat energy to the loss to surroundings, so we should provide a lagging or insulation, like provide lagging or insulation around the block so it won't lose energy to the surrounding, and allow the block to cool down and then repeat the experiment, because at a higher temperature, more greater chance it will lose energy to the surrounding. So providing lagging, and if we, because the idea is that whenever experiment is done, if say the room temperature is 25 and the block temperature, when we did like 13 degrees, and when we supply the heat energy, temperature rises to say 22 degrees. So it won't take energy from the surrounding, because heat energy transfer from hot object to cold object. So it will always absorb energy, not lose energy to the surrounding. So when we do this experiment, what we can do, we can repeat this experiment. We can do this experiment at a temperature which will always remain below the, like in one sequence, like it will remain below the room temperature, so it won't lose energy to the surrounding. It will always absorb energy from the surrounding. So it won't make too much difference in the temperature values. And if we repeat the experiment, we can repeat this experiment, allow the block to cool down, because when the block will cool down, the temperature will be low, so rate of energy lost to the surrounding will be minimized. If the block is at 20 degrees and another block is there, like you did the experiment and you're doing it 40 degrees. So block will lose more energy to the surrounding. So allow the block to cool down and repeat. Sorry. So we allow this block to cool down and we repeat the experiment. About this one, this is related to latent heat. For IGCSE students, you don't have this. For calculation is not there. Don't think latent heat is not there. Latent heat means energy needed to change the state. It is there. Like they can ask for melting, they can ask for boiling, but they won't ask for calculation part won't be there for you. But for GCSE students, they will have this calculation as well. Figure 4.1 shows apparatus melting of an ice. Describe how you could use this apparatus. Assume that the ice is at 0 and the stopwatch are reliable. State all the readings. So what we need, we want to calculate the latent heat. So energy is equals to mass into latent heat. So if we need the latent heat, specific latent heat, it will be energy divided by mass. They mentioned the power of the heater is known here, which is a 60-watt heater. So whenever you're using electrical heater, energy is power into time. So it will be power into time divided by mass and latent heat. So what readings we need to calculate the latent heat? Power is already there. It's already mentioned it is a 60-watt heater. So we don't need a power. Power is already with us. We need a time. So we'll use a stopwatch. We'll record the time for the ice to melt. And what we'll measure? We'll measure the mass of the beaker when the constant dripping start. Because when the constant dripping start, it means that all the ices start to melt. What does it mean, constant dripping? Like every second, one drop is coming out from the funnel, or every second, two drops are coming out from, like constantly the water drips into a beaker. So what we will do, we will switch on the heater. And we will wait until the constant dripping start. Why we wait until the constant dripping start? Because once the constant dripping start, now we are sure that this whole ice is start to melt. Ice is melting even before the constant dripping. The ice is melting, but not all the ice may have a 0 degree before constant dripping. Once we reach a constant dripping, it means like maybe these are ice cubes or crushed ice which is nearby the heater might be at 0, but the ice here might be at -4. So once all have 0, like all will be at 0 degrees centigrade, now the constant dripping start. So we switch on the heater, the ice is melting, but we wait until a constant dripping start. And once a constant dripping start, now we are sure that all the ice is having a 0 degree centigrade. And then what we will do, we'll record the time. And measure the mass of ice melt. We don't need power here because already we have the power in the question. That's why we don't need the power. Then As I mentioned, it's not for IGCSE student, because 2023 syllabus, you don't have this latent heat. Formula is not there. Again, I repeat, formula is not there, but they can ask what happened when the substance is melting, why the temperature does not change, what happened to the forces between the particle when the substance is melting. These type of questions still are there, but you don't have the calculation part. So we need the expected time. So I just write a formula here. I will, because we have the formula whenever a state change, energy is mass into latent heat. And we use heater, so it is power into time, mass into latent heat. So we have the power of the heater, which is 60. We have the mass of the ice, which is melted. We have the latent heat. If mass is in gram, latent heat should be in gram. So we work out the time, expected time, which is 680 seconds. Okay. So 680 seconds when you solve this. When experiment is carried out, the ice melts slightly less time than expected. State one reason. Like, we calculated that this ice should melt in 680 seconds, but it melts much quicker. Like, it might take maybe 400 seconds or 300 seconds to melt this ice completely. Why? What is the reason? Or what might be a reason? So ice gain energy from a surrounding, and ice always gain energy from surrounding, because the surrounding, usually we have room temperature is higher than 0. So it gain energy from surrounding. It took energy from outside, or beaker, or a conical funnel, basically, not conical flask. And suggest a modification. So if we don't want it to gain heat energy from the surrounding, what we should do, we should provide a lagging, or
We can
yeah, yeah, insulated lid is usually, if it was a container, then we provide a lid here. We can use any insulating material so it does not lose energy, like absorb energy from the surrounding. No, not lid here. You cannot mention a lid. It's only like insulate or wrap, use aluminum foil, which is a reflecting surface. Then this question, experiment for a latent heat of vaporization, 34,500 joule is used for 15 gram, which was originally at 100. A second experiment, 600 joule of energy was lost. So out of 34,500, 600 joule is lost. So 29,900 will be there. So if we need a latent heat, energy is mass into latent heat. So out of this one is lost. So how much energy will be there? It will be 29,900. Mass is 15 and latent heat, we just divide and we get the latent heat. In question 17, these type of questions, still you will have such questions in which you have to plan experiment to find specific heat capacity. A student want to estimate the specific heat capacity of iron. The power of the heater is known. State 4 readings. Look, you modify the formula whenever the specific heat formula E is equals to Cm del 13. So if I need specific heat, it will be energy divided by M del 13. An electrical heater, the energy is power into time. So I can say power into time divided by M, and delta T is T2 minus T1. So if I need specific heat capacity, power, they already mentioned we have. So what I need time. I need the mass of a block. I need the initial or the starting temperature, and I need the final temperature. Because they ask what readings we have to take, temperature change we will calculate. So initial and a final temperature we will measure. Is it clear, this one?
Yes, sir, clear.
Then the equation, just now I mentioned what equation we'll write for this, that specific heat capacity. It's in according to the question, power into time, mass, and temperature change. In some books, the temperature change is given delta theta. You can write delta T or delta theta. It's fine. Both are correct. Explain the value. Um, Normally, why the value obtained by this apparatus is higher than the actual value. Because what actually happened, the same reason what we have discussed in question 14. What usually happen when we supply the heat energy to a block, it become hot and it lose energy to the surrounding. So as it lost energy to the surrounding, the temperature change will be small. As a result, the specific heat capacity will be higher. So heat loss to the surrounding. No, thermometer reading is, it can be avoided, like we should look perpendicular and avoid, but for specific heat capacity experiments, why whenever we do such experiment, we always or usually get the higher value than the expected, because the formula C is equals to E divided by M delta T. As the block loses energy to the surrounding, so temperature change will be small. As a result, the specific heat capacity will be higher. So you will mention that heat loss to the surrounding, which reduce the temperature change, and it will give higher value. State one addition to the apparatus that would help you to improve the accuracy. How we lagging the block and insulating material, or supply the heat energy, or keep the temperature of a block always below the room temperature. Like when we are supplying heat energy, it should not exceed, because otherwise if the temperature of a block is more than or higher than the room temperature, it will start to lose energy to surrounding. So say surrounding temperature is 25. So we cause a temperature change, but keep the temperature change within the, like less than the surrounding. So we started the experiment at 20 and we keep it at 23. So it won't lose energy to the surrounding, it will absorb energy from the surrounding. But usually for such questions, the best answer is lagging or insulation. See, do differences between evaporation of water and boiling of water, how they're different from each other.
Evaporation shows bubbles while boiling shows bubbles while evaporation doesn't show.
Evaporation can happen at any temperature. Boiling occur at a fixed temperature, that's right. And the evaporation happen only at the surface. Absorbing the energy, it will affect the result, but it won't affect the result too much as compared to energy lost to the surrounding. When it lose energy to the surrounding, the results have a greater difference between the practical and experimental value. Bubbles are there, no bubbles. Then the without calculation questions will be there for those IGCSE students, a specific latent heat of vaporization. This type of question will be there. Why this energy is needed to boil water and why temperature of water does not change. And it's of 3 marks. So what we'll mention, why the temperature is not changing and what happened. So when we supply the energy, energy is used to break the intermolecular forces. And the particle move away from each other, but their kinetic energy does not change. So the answer here, energy is used to break the bonds between the particles or molecules. The particles move away from each other, particles or molecules. Without changing the kinetic energy. So the temperature, you can mention kinetic energy or you can mention speed. So the temperature does not change. In a lab, we are providing latent heat is there. Latent heat of vaporization means the state is changing. So energy is equals to mass into latent heat. And the power is there. Whenever power, so energy is power into time. So in place of energy, we can write power into time. So we have the power. We have it's gram per second. So time is 1 second. We have time as well. We have the mass as well. So we can work out the latent heat. Just substitute the values and you will get the latent heat, which is 2400 joules per gram. But again, as I repeat for you, IGCSE students, you don't have to learn this formula. Only the explanation is important, like what happened when the state changes. In question 19, figure 4.1 shows a student attempt to estimate the specific latent heat of fusion of ice. So what will happen? The ice will absorb energy from water. The water temperature decrease and the ice will start to melt. 3 mass readings are taken. Write down the description of the other 2. So first, student measure the mass of the beaker, stirrer, and thermometer. Like first he measure the mass of a beaker, the stirrer, and thermometer. Then he will add water. 3 mass readings only. Like then he will add water. So it will be a mass of a beaker plus stirrer plus thermometer plus water. And what is the next reading? The mass of a beaker, stirrer, thermometer, water, and ice. If you want the mass of a water, he subtract reading 1 and reading 2. If you want to find the mass of an ice, reading 2 and reading 3, he will subtract. Or it can be first ice and then water. Write down an equation which student could use to find energy loss by the water. As you can see, there is a change in temperature. It changes from 20 to 0. So whenever there is a change in temperature, the formula for energy, we don't have to subtract this. The question is what values, what reading student will take. So first student take the reading of a mass, beaker, stirrer, and thermometer. Then he took the reading of a mass of stirrer, thermometer, beaker, and water, and then stirrer, thermometer, beaker, water, and ice. So because there is a change in temperature, so energy is equals to Cm delta T. And here the ice start to change the state, so energy is equals to M into L. Mass into latent heat. The latent heat of fusion you need, you have the energy, you have the mass, you can work out the latent heat. Energies, whenever there's a change in state, energy, mass into latent heat, you have the energy, you have the mass, you just divide and you will get the latent heat here. So just 2 reasons why the value is only approximate value. Why this value won't be accurate when we work out the latent heat in this experiment. So the previous answer 426.6. Okay. Here, what is actually happening? That water is a hot object, ice is a cold object. So heat energy transfer from water to ice. So ice gain, what we consider the water is losing energy and the ice gain energy. So all the energy from water transfer to ice. But in practical, what might happen? The heat energy absorbed from surrounding, like ice may absorb energy from surrounding. That is one thing. And another thing, water might lose energy to the surrounding as well. Or you can also say a water might gain energy from the surrounding. That will also lead to an error. So ice absorb energy from the surrounding. What we assume it is only absorbing energy from the water. Even you can mention like it may absorb energy from the stirrer or even from a thermometer. That's why the practical value will be different from the calculated value. In question 20, is it clear, the last one, the two reasons? Question 20. A certain substance is in solid state at minus 36. So it was solid at minus 36. Then you can see that temperature does not change here. So what happened? First, we will have a solid. Here, a solid turned into a liquid. And then it's liquid. And again, the temperature does not change. It means the liquid is turning into a gas. Whenever the temperature does not change, it means the state is changing. So this region state is changing and 121 state is also changing. Latent, what is meant by the term latent heat? You have to know this definition. The term latent heat means energy needed to change the state without changing temperature. That's right. So amount of energy which we need to change the state without changing a temperature, we call that as a latent heat. State the time at which the energy supplied as a latent heat of fusion. Fusion means when a solid is turning into a liquid. So what time interval? For what time interval a solid is turning into a liquid? For how much time? It is for 8, it's starting with 2 and ending at 14. So how many minutes? So it will be 12 minutes. Because for 12 minutes, a solid was turning into a liquid. Then how much energy is supplied? We have the power and we have the time. So energy is power into time. Power is given in kilowatt. It means it will be 2000. And the time is in minute, which is 4 minutes. You have to convert it into seconds. So you will multiply by 60. So you will get how much energy is supplied. And then specific heat capacity of a substance. So what is this answer? This one? 2000 times 4 into 60. How much energy is being supplied? 480,000. So 480,000 joule of energy supplied. And that energy supplied is used to change the temperature. From 80, specific heat capacity is there. So that energy which we supply, it causes a temperature change. So how much is the temperature change from 8 to 22 minutes? The temperature change will be 75 minus 32. So we'll use a formula because in the question we have specific heat capacity is given. So specific heat capacity is given. We'll use the formula E is equals to Cm delta T. We just substitute for 480,000. Specific heat is 1760. The mass we don't know and the temperature change is 75 minus 32. So this will divide, we'll get the mass which is 6.3 or 6.34. So 6.34 is the mass of this. The